There is a rock sitting on Mars right now. It's inside a sealed metal tube about the size of a piece of chalk, drilled out of a stone the team named Cheva Falls in the summer of 2024. The rock has small dark markings in it. The people who found them call them poppy seeds and leopard spots. On Earth, patterns like that would be a textbook signature of microbial life. Last September, after a year of careful review, NASA's official position became that the sample contains what they call a potential biosignature. They're extremely careful with the word potential. Nobody's saying life. Not yet. But the tube is still there. It's sitting on the surface of a planet that died roughly 3.5 billion years ago, and the earliest we might get it home is somewhere in the late 2030s. Tonight, we're going to talk about that rock. But not only about that rock, because Mars isn't the only dead world. It may not even be a rare one. What we're doing tonight is sitting with a question that doesn't get asked very often because it makes people uncomfortable. The universe, as far as we can currently see it, contains a confirmed inventory of just over 6,000 worlds beyond our solar system, and a credible estimate of hundreds of billions more in our galaxy alone. The natural assumption is that some fraction of those should be alive. Someone should be home. But the more we learn about what it actually takes to keep a world habitable, the more it starts to look like the real story isn't about life starting, it's about life lasting. By the end of tonight, you're going to see the night sky a little differently. Not as a place that's empty, as a place that might be very, very full of something quieter than we expected. Something that already happened, something that ended. Here's where most people get the universe wrong. When they think about whether anyone is out there, they imagine two doors. Door 1, the cosmos is teeming with company and we just haven't run into them yet. Door 2, the cosmos is empty and we're alone here, and that's just how it is. Those are the two answers people argue about. There's a third door, and that's the one we're walking through tonight. It's the possibility that the universe isn't empty at all. It's the possibility that it's full of worlds where the conditions for life arrived and then left. Worlds where life may have started and then stopped. Worlds with the light still on and nobody home. Before we go further into this, if you're finding yourself sitting with what was just said about that sealed tube on Mars, take a moment to like the video or subscribe. It genuinely helps this channel reach more people who actually want to think about this stuff at 3 in the morning, instead of being yelled at about it. That's it. Now back to it. The number to sit with first is 6,087. That's the count of confirmed worlds outside our solar system as of January of 2026, listed in the NASA Exoplanet Archive, which is the official register where confirmed discoveries get logged. NASA crossed the 6,000 mark in September of 2025. To put that in scale, there are about 195 sovereign countries on Earth. We have more confirmed worlds beyond our solar system than we have countries here by a factor of 30. And those are just the worlds we've actually managed to detect. The real number, the estimated number, is much larger. There are roughly 200 billion stars in the Milky Way. The working assumption, based on data from the Kepler and TESS missions, is that nearly every star has at least one planet. Some have many, so when astronomers do the arithmetic, they end up with somewhere in the hundreds of billions of planets in this galaxy alone. Of those, the latest estimates put the number of planets sitting in the habitable zone, the region around a star where liquid water could theoretically exist on the surface, somewhere in the tens of billions. That's a lot of worlds, so why is it so quiet? The first thing to understand is that habitable zone is a misleading term. It only means liquid water could exist there, in principle. It doesn't mean water is there. It doesn't mean it ever was there. It doesn't mean the planet has an atmosphere capable of holding water. It doesn't mean the surface temperature is currently within liquid water's range. It just means the orbit sits at roughly the right distance from the star. So when you hear that there might be tens of billions of habitable zone planets in this galaxy, what's actually being said is that there are tens of billions of orbital slots where conditions aren't ruled out. The conditions could still be ruled out by 1,000 other things, and very often are. Out of the 6,000 confirmed exoplanets we have, most of them are nothing like Earth. The first ones we found were hot Jupiters, gas giants so close to their stars that their atmospheres glow. They're the easiest to detect, which is why we found them first. Then came super-Earths, rocky worlds bigger than ours, often in orbits so tight that a year there lasts a few Earth days. Then came tidally locked planets, where one side of the world faces the star forever, and the other side faces away forever, leaving a permanent sunlit hemisphere baked into rock, and a permanent dark hemisphere frozen so cold the air can fall as snow. Then came planets in scorched orbits, planets with no atmosphere left, planets where the surface gravity is too high for a human heart to keep beating in. When you look at the catalogue of what we've actually found, the planets that resemble Earth in any meaningful way are rare. Out of 6,000 confirmed worlds, the number that could be described as roughly Earth-sized, in roughly the right orbit, around a roughly stable star, is in the low dozens. So part of the silence is just that. Most of these worlds were never going to talk to us in the first place. They couldn't. They don't have the chemistry, the temperature, the air, the time. They are stones in space. But that's only part of it, because the truly strange thing isn't the worlds that never could have been alive. The strange thing is the worlds that maybe could have been. The Earth-like candidates, those are out there in real numbers, even by the most conservative estimates. And out of those we have no signal, no radio call, no optical flash, no chemical fingerprint we can identify as life. Nothing. That's the silence that's hard to explain. The silence of the worlds that should, by any decent statistical argument, have something on them. There's an image I keep coming back to when I sit with this. The universe, at least the part we can see, isn't quiet because nobody ever existed in it. It's quiet the way an old library is quiet. You walk in at night, and the lights are off, but the building is still there. The shelves are still there. The books are still there. Every spine you pull off has a real author behind it. Real ink, real pages. The library wasn't built empty. Somebody filled it. But it's been a long time. The writers are gone. The readers are gone. The lamps overhead have burned out one by one. The building has gone quiet. The books are still there, the voices aren't. When astronomers find a planet through the Kepler mission, what they actually see is a star that dims a little, every few days or weeks, in a regular pattern. The dim is the planet crossing in front of the star, blocking a fraction of its light. That's it, that's all we see for most of them. We never see the planet directly, we see a slight repeating shadow, and from that shadow we work out how big the planet is, how close to its star it sits, how long its year lasts. We don't see what's there, we see that something is there. And then we go to the next star. That's what most of exoplanet science looks like. You stand outside the library. You can tell, from the shape of the shadows on the wall, that the building has shelves and aisles and corners. You can guess at the number of books, you can guess at their size, but you can't go in. And what you mostly can't do is tell, from the outside, whether anyone ever read them. The other thing to understand about the silence is the timing. Even if every Earth-like world out there had developed intelligent life, the odds of any two civilizations existing at the same moment in a galaxy whose history spans more than 10 billion years are slim. Human radio communication has been a thing for about 100 years. Recognizable human civilization, somewhere around 10,000. Anatomically modern humans, around 300,000. The Earth has been habitable for about 4 billion years. If you compress all of Earth's habitable history into a single calendar year, the entire span of human existence shows up in the last 90 seconds before midnight, on December 31st. Modern science fits in the last second. Now picture a galaxy where every habitable world has its own version of that calendar, started at a different time, ending at a different time, with most of the calendar quiet and ordinary, and only a few seconds in each year where anything loud is happening. The chance of 2 of those calendars overlapping in those few loud seconds is small. Most of the time, you'd reach into the universe at random, and you'd pick a world that either hadn't started its civilization yet, or had finished it, or had never had one at all. Silence isn't proof of empty, it's proof of timing. There's a phrase astronomers sometimes use, half joking, when they're talking about all of this. They call it the Great Quiet, not the Great Filter, which is a specific argument about what stops civilizations from growing. The Great Quiet is just the observation, it's just the listening. The fact that the receiver is on and the signal level is essentially zero, and has been essentially zero for as long as we've been able to check. Some of that quiet might be that nobody is out there. Some of it is almost certainly that somebody was and isn't anymore. The library, in other words, is real. The shelves are full, the lights are off. Whether anyone is still inside is a question we don't have a tool sharp enough to answer yet. What we do have is the shape of the building and a sense, growing every year, of how many rooms it contains. If you want to know what one of those quiet rooms in the library looks like up close, we don't have to travel far. We already have one. It's the planet next door. Mars is the easiest dead world to talk about because we can see it. You can step outside on the right night, look up, find the small steady reddish light in the constellation we happen to call wherever it is that month. And there it is, the 4th planet from the Sun, the next door neighbour, the one you don't have to imagine because it's actually there. For most of human history, Mars was a wandering light in the sky and a name for a god of war. It became a place sometime in the late 1800s when telescopes got good enough to show that the reddish dot was a world, with polar caps that grew and shrank with the seasons and dark patches that some astronomers convinced themselves were vegetation. By the late 1800s, the Italian astronomer Schiaparelli was reporting straight lines across the Martian surface, which the American astronomer Percival Lowell convinced himself were canals dug by a dying civilization to move the last of their water from the poles to the equator. None of that turned out to be true. The lines were an artifact of the eye trying to make sense of fuzzy images. The dark patches were dust and stone. There were no canals. But the idea of Mars as a dying world turned out to be closer to right than anyone realized. The Mars we have today is by any reasonable definition dead. The surface temperature averages about -63 degrees Celsius. That's roughly the coldest temperature ever recorded in Antarctica, except that on Mars that's the average, not the extreme. The atmosphere is so thin that liquid water on the surface would boil and freeze almost at the same instant because the pressure is too low to keep water in its liquid state. Standing on the surface of Mars today, with a perfect spacesuit, you would still feel the cold soak into the soles of your boots within minutes. The sky overhead would be a pale butterscotch colour, not blue, because there isn't enough air to scatter light the way Earth's atmosphere does. The sun, when you found it, would look smaller and dimmer. The horizon would feel close because Mars is a smaller world and the curve of the ground falls away faster. It would feel like a place that something used to live in. That feeling, it turns out, is correct. Here's what we know. Mars used to have a magnetic field, a real one, a planet-wide one, generated by a molten metal core spinning at the center of the world, the same way Earth's core spins now. That magnetic field acted as a shield. It deflected the solar wind, which is the constant stream of charged particles the sun throws off in every direction. The shield meant that whatever atmosphere Mars had, it could hold on to. The shield meant water on the surface could stay water. The shield meant a sky thick enough to feel like a sky. Then the shield went down. The current best estimate from paleomagnetic analysis of Martian meteorites and remote magnetic measurements of the crust is that Mars's global magnetic field collapsed roughly 3.9 billion years ago. That date has been pushed and pulled by different studies in the past few years. The most recent work including a high-profile paper out of Harvard published in 2023 and reaffirmed by follow-up studies through 2025, suggests the field may have lasted slightly longer than people used to think, but the headline is the same: the core cooled, the dynamo stopped, the shield went away. After that, the atmosphere started to bleed. Slowly, not in one event. Over hundreds of millions of years, the solar wind picked at the top of Mars's atmosphere, knocking the lighter molecules off into space, one at a time, in a process so gradual that if you'd been standing on the surface watching, you wouldn't have noticed anything different from one century to the next. But the budget was negative. More air was leaving than was being replaced, and eventually the bank account ran out. Today, Mars's surface pressure is somewhere between 1 and 14 millibars, depending on altitude and season. Earth's surface pressure is 1,013 millibars, so Mars currently has less than 1% of the air pressure we have here. To find air that thin on Earth, you would have to go up to about 30 kilometers above the surface, which is about 3 times higher than a passenger jet flies. That's the kind of air Mars now has at ground level. But there was a window, there was a long window, and inside that window, things happened. The Curiosity rover, which landed in Gale crater in 2012, has spent more than a decade slowly driving up the slopes of a mountain in the middle of that crater, examining the rocks layer by layer. Gale crater was a lake, we know that now. The layered mudstones, the river-worn pebbles, the salt deposits, the clay minerals that only form in standing water, all of it tells a story. Around 3.8 billion years ago, this part of Mars was full of liquid water. There was a deep lake fed by rivers. The lake stayed for a long time. The mineral evidence suggests it persisted, on and off, for something like 700 million years, with the last clearly habitable conditions winking out somewhere around 3.1 billion years ago. 700 million years is a length of time that's hard to hold in your head. Life on Earth, in any complex form anyone could recognize, has only existed for about 600 million years. The Cambrian explosion, when animals with hard parts first showed up in the fossil record, was about 540 million years ago. Which is to say, Mars's habitable window on the surface lasted longer than the entire history of complex animal life on Earth so far. And on Earth, in the same era, life had already gotten started. The earliest convincing evidence of microbial life on this planet shows up in rocks around 3.5 billion years old. And there are some hints, debated but real, of biological signatures going back maybe 3.8 or 3.9 billion years, which means that the two planets were running the same experiment at the same time. They had liquid water at the same time. They had atmospheres at the same time. One of them, we know for sure, started growing life. The other one had every ingredient to do the same thing. And then, somewhere around 3 billion years ago, the conditions on Mars stopped being friendly. Which brings us back to the rock. The Perseverance rover landed in Jezero crater in February of 2021. Jezero, like Gale, used to be a lake. You can see in the satellite imagery the fossilized remains of a river delta where ancient water flowed in from the surrounding highlands and dropped its sediment in fan-shaped layers. Perseverance was sent there specifically to look for biosignatures. It's been driving across that delta, taking samples, since it arrived. In July of 2024, Perseverance drilled into a rock the team named Shiava Falls. The drill produced a small cylindrical sample sealed in a metal tube, which the team named Sapphire Canyon. The team noticed something unusual right away. The rock contained small nodules, dark-coloured, distributed through the sediment in patterns that on Earth would be unusual. Some looked like poppy seeds, some looked like leopard spots. Chemical analysis, done with the rover's instruments, identified the nodules as concentrations of iron phosphate in a mineral form called vivianite, along with iron sulfide in a mineral form called greigite. On Earth, that combination is interesting. Vivianite and greigite together with organic carbon in mudstone, in those kinds of patterns, are what gets produced by certain microbes when they do their chemistry. Specifically, when iron-breathing bacteria pull energy out of sediments by moving electrons around between iron and sulfur compounds. The patterns Perseverance saw in the rock it sampled are the kind of patterns a textbook would call a microbial biosignature. The paper describing the find was published in Nature in September of 2025, after a year of careful internal and external review. The authors are extremely careful with their language. The phrase they use is potential biosignature. They list the alternative explanations. The patterns could be produced by chemistry that isn't biology, by certain volcanic processes, by water-rock interactions that don't involve life at all. They don't claim they found life on Mars. They claim they found something that, on Earth, would be the first thing you'd point to as evidence of life, and that other explanations remain on the table. The sample is sitting on the surface of Mars right now, in its sealed tube. The Mars Sample Return mission, which would bring it home for analysis in laboratories that can do tests no rover can, is in flux. The original schedule, which would have had the tube back on Earth, is now under budget review and architectural change. The current best estimate for retrieval is somewhere in the late 2030s, possibly later, which means that the most consequential rock sample in the history of our species is going to sit on the surface of another planet for at least another decade, waiting for us to come get it. In the meantime, all we have is the photograph. There's an old idea about photographs that they're not so much images of people as they are of moments. The person you photograph today will keep aging. The moment, frozen on the film, doesn't. So you end up holding in your hand a small rectangle that's a piece of time separated from the person it came from. That's what Shayava Falls is. A piece of time. Maybe a piece of Martian time, when something was alive. Maybe a piece of Martian time, when no life was ever present, and the rocks just happened to assemble themselves into patterns that look like life would have made them. We don't know. The image is real. What it shows is still being worked out. If you've ever moved into a house that someone else used to live in, and you've gone up into the attic, you know the feeling. There's a box up there. The box has photos in it. Real photos, real people, real faces, in clothes you don't recognize, in rooms you don't recognize, in places you've never been. You're holding pictures of people who walked through your hallway and ate in your kitchen, generations before you bought the property. They're not your family, they're just people. The fact that they were there, doing ordinary things in the same physical space you now live in, is hard to absorb the first time you really notice it. Mars is like that attic. You climb up there expecting dust, expecting nothing, and instead you find a photo album. The pictures are real. They are of someone you've never met, and the camera that took them stopped working a very long time ago. That's the situation we're in with Mars. The rock in the tube is the latest photograph from the attic. There may be others, there almost certainly are. The Mars 2020 mission is one of dozens of missions, robotic and orbital, that have been studying this planet for 60 years. We've been knocking on the door for 60 years. Sometimes the door rattles. Sometimes a window opens. Mostly the house is quiet. The wind blows red dust against the porch. Mars's porch light is still on. We've been ringing the doorbell for 60 years. Mars is the obvious dead world. The one that's harder to think about because it's our actual twin, the one we don't usually let ourselves consider, is the planet on the other side of us, the one we usually skip past in school, the one we file under hot rock and stop thinking about. That's Venus. We don't think about Venus the way we think about Mars. Mars gets all the cultural attention. Mars is the rover planet, the future colony planet, the one people put on the cover of magazines next to a square-jawed person in a spacesuit. Venus is the one we mostly skip. You learn about Venus in school for about a week. It's the one with the runaway greenhouse. It's the one that's too hot, the greenhouse gone wrong example. The lesson where the teacher tells you that's what happens if a planet gets too much carbon dioxide, and then you move on. That telling is wrong, or at least it's missing the most important part. Venus, on paper, is Earth. Almost exactly Earth. It has roughly the same diameter as our planet, the same mass, the same density. It formed at roughly the same time, out of the same protoplanetary disk, from the same general mix of materials. It sits inside the inner solar system. It's our sister world by every standard astronomers used to mean by the term sister world. If you grabbed a stranger and showed them the basic specifications of two planets, one labelled Earth and one labelled Venus, and asked them which one supports life, they'd have no way to tell. And here's the part that I genuinely think people should sit with for a minute. Venus may have been habitable, with liquid water oceans on the surface, for as long as 2 to 3 billion years. That's not a wild speculation. That's the conclusion of climate models run by NASA's Goddard Institute for Space Studies. The Way and Del Genio simulations, published originally in 2016 and refined in subsequent papers, take what we know about Venus's likely early conditions, run a three-dimensional climate model forward in time, and find that under reasonable assumptions about cloud cover and rotation, Venus could have had a stable temperate climate with surface oceans for somewhere between 2 and 3 billion years before it tipped into the state it's in now. 2 to 3 billion years. To put that in scale, life on Earth has been around in any complex form, anything more than single cells, for about 600 million years. Venus, on this timeline, had liquid surface oceans for longer than complex multicellular life has existed on Earth. 5 times as long, give or take. There was on the surface of that planet an environment that under any reasonable definition would have been habitable for an amount of time that dwarfs the existence of any animal anyone has ever named. Whether anything used that habitat is another question entirely. We have no fossils from Venus. We have at this point no surface samples from Venus. The few Soviet landers that touched down on the Venusian surface in the 1970s and early 1980s lasted on average less than 2 hours before the heat and pressure killed them. The longest survivor, Venera 13, lasted just over 2 hours. The pictures it sent back show a flat tan landscape of broken rock. The sky overhead a heavy sulphurous yellow. No animals, no plants, definitely no civilizations. But the question isn't whether anything is there now. The question is whether anything was 2 billion years ago, when the planet might have looked completely different. Then, somewhere around 700 million years ago, the conditions on Venus changed. The triggering event is debated. The leading candidates include a massive global resurfacing event, where the entire surface of Venus was repaved by volcanic activity in a relatively short geological window, possibly within 50 to 100 million years. There's also the steady brightening of the sun, which has been increasing in luminosity by roughly 10% every billion years over its life. There's the possibility of a runaway volcanic outgassing episode that pumped enormous amounts of carbon dioxide into the atmosphere over a relatively short time. There's a possibility that more than one of these things happened together and crossed a threshold the climate system could no longer balance. Whatever the trigger was, the climate flipped. Water vapor, which is itself a powerful greenhouse gas, trapped more heat in the atmosphere. The hotter atmosphere held more water vapor, which trapped more heat. The oceans began to evaporate. The hotter the atmosphere got, the more the oceans evaporated, the more water vapor entered the atmosphere, the hotter the atmosphere got. That feedback loop is what scientists mean by a runaway greenhouse. By the time the runaway finished, Venus's oceans were entirely gone. The water vapor in the upper atmosphere got broken apart by solar ultraviolet radiation. The hydrogen, being light, drifted off into space. The oxygen, being heavier, mostly bonded with surface materials and got locked into rocks. The carbon dioxide, which had been dissolved in the oceans and locked up in rocks, was now free in the atmosphere, and the atmosphere just kept thickening. Today, the surface temperature on Venus averages about 462 degrees Celsius. That's about 864 degrees Fahrenheit. Hot enough to melt lead, hot enough that you don't need to imagine standing on it. You don't get to stand on it. You'd be dead in less than a second. The surface pressure on Venus is about 92 times Earth's atmospheric pressure. That's the pressure you'd feel at the bottom of about 900 meters of ocean. Not 900. To find a place on Earth with pressure that crushing, you'd have to go deeper than any human submarine has ever taken people. The Soviet landers that survived for those few hours did so because they were essentially deep-sea pressure vessels, built with hulls thick enough to handle the weight of an ocean's worth of atmosphere. The sky overhead, if you could somehow see it, is a thick yellow gloom full of clouds made of sulfuric acid. The clouds rain, but the rain never reaches the surface. It evaporates back into the atmosphere on the way down because the lower atmosphere is so hot that liquid sulfuric acid can't stay liquid in it. So the sky has weather, and the weather has acid, and the acid never lands. This is what Venus is now, a place where lead would puddle on the ground, a place where the air weighs 92 times what our air weighs, and that air is poisonous and corrosive and full of acid rain that never reaches the surface, a place that is by any reasonable definition, hell. The way I keep coming back to this is something everyone has done at one point or another. You put a pot of water on the stove. You turn the burner on. You walk away, planning to come back when it boils. But you get distracted. You take a phone call. You answer the door. You forget about the pot. When you remember, you walk back into the kitchen and the bottom of the pot is glowing and the water is gone. That's Venus. For a long time, the pot was fine. The water simmered. You could still see the surface of the water. You could still see the bottom of the pot. You could still cook in it. Then, slowly, the water level dropped. Then the pot was dry. Then the pot was glowing. Venus has been a glowing pot for 700 million years, and the burner will not turn off. Here's the part that, for me, makes Venus the harder world to think about than Mars. The oceans don't completely vanish. They leave a trace. If you look at the chemical composition of Venus's atmosphere with a sensitive enough instrument, and you measure the ratio of two kinds of hydrogen in the upper atmosphere, you find something that doesn't make sense unless Venus used to have a lot more water than it does now. There's regular hydrogen, the kind with one proton in the nucleus, and there's deuterium, the heavier kind with a proton and a neutron. Deuterium is rare. On Earth, it makes up about 1 part in 6,400 of the hydrogen in our oceans. On Venus, the ratio of deuterium to regular hydrogen is roughly 150 times what it is on Earth. That's not a small number. That's the kind of number that has only one good explanation. Light hydrogen escapes into space more easily than heavy hydrogen, because light things move faster at any given temperature, and the lightest things in the upper atmosphere are the ones that get knocked off into space by solar wind and ultraviolet light. So if you start with a planet that has both kinds of hydrogen mixed in its oceans, and you boil those oceans into the upper atmosphere, and you let solar radiation work on that water vapor for a few billion years, the regular hydrogen gets stripped away faster, and the deuterium hangs around. Over time, the ratio of heavy to light hydrogen in the remaining atmosphere goes up. So when you measure Venus's atmosphere today, and you find 150 times Earth's deuterium ratio, what you're measuring is the chemical fingerprint of an ocean's worth of water that boiled into space billions of years ago, with the lighter component carried off first, leaving the heavier component behind in the air. The water is gone. The trace of the water is not gone. There's a kind of grief that comes with that detail when you sit with it for a minute. We don't usually think of planets as having ghosts, but Venus has one. It's chemical, it's measurable, it's there. The ocean that used to be on Venus is, in a real sense, still hanging in the air, just as a ratio of isotopes, just as a number on a spectrometer, the shape of an absence. We could detect that ratio from Earth, with the right telescope 60 light-years away. If Venus existed in a system around another star, and we had the right instruments pointed at it, We could measure the deuterium signature in its atmosphere, and we could say with high confidence that this planet used to have a lot of water and now doesn't. We could say it without ever going there. We could say it without ever sending a lander. We could read the obituary from a distance. There may be planets out there, right now, that we have already done that with. We may not have realized what we were looking at. The hardware to measure this kind of thing reliably across light years is just now coming online with the James Webb Space Telescope and a generation of ground-based, extremely large telescopes coming in the late 2020s and 2030s. The first time we read a Venus-like ghost on an exoplanet, we won't be making a discovery. We'll be confirming something the universe has been recording on its own. The fingerprint of a former ocean. Venus's porch light is still on. The light's been on for 4 billion years. The house burned down inside. So now we have two dead worlds in our own neighborhood. Mars, killed by a cooling core and a vanished atmosphere. Venus, killed by a runaway greenhouse and an ocean's worth of water boiled into space. Different deaths, same result. Two planets, the same age, the same materials, the same construction, the same starting conditions, one of them in the dust, one of them in the fire, Earth in between. Which raises a question that ought to make anyone uncomfortable. How stable is any habitable window, anywhere, if two of the three rocky planets that started inside the Sun's habitable zone have already lost their habitability by completely different mechanisms? What does that tell us about the third one? That's where we have to look next. Because as it turns out, the habitable zone itself is not a place you can plant a flag in and stay forever. It moves. When people first hear about the habitable zone, the image that gets planted in their head is a kind of permanent neighborhood. You imagine a ring around a star, and inside that ring it's just right, and outside that ring it isn't. The planets inside the ring are the good ones. The planets outside the ring are too hot or too cold. Earth is inside the ring, and that's why we get to exist, and that's basically the end of the story. Almost none of that is right. The habitable zone is real. The math behind it is real. It is, very specifically, the range of orbital distances from a star at which liquid water could in principle exist on the surface of a planet, given some basic assumptions about atmosphere and reflectivity. For our Sun, the habitable zone today is in the most commonly used estimates, the orbital region between about 95% of Earth's distance from the Sun and about 170% of it, roughly. Different models give slightly different boundaries depending on what assumptions they make about clouds and atmospheric composition. But the habitable zone moves. It moves because stars change. Stars are not steady. They look steady to us because human lifespans are short and stars change slowly. But over billions of years, every star brightens, cools, expands, and eventually dies. The brightening part is the part that matters here. A main sequence star, the kind our Sun is, the kind most stars in the galaxy are at any given moment, gets gradually brighter as it ages. Hydrogen in its core fuses into helium. The core becomes slightly denser. The pressure goes up. The temperature goes up. The fusion rate goes up. The star puts out more energy. Year by year, the increase is invisible. Over billions of years, it adds up. The Sun has brightened by roughly 30% since the Earth formed. That's not a minor adjustment. That's the difference between a comfortable indoor temperature and a fever. If the Sun today were as faint as it was when Earth was new, the planet would be a frozen ball. There's a paradox built into that fact called the faint young sun paradox, which is a fancy way of pointing out that the Sun used to put out a lot less light, and yet there's clear geological evidence of liquid water on Earth's surface as far back as 4 billion years ago. Somehow, the early Earth was warm enough for water despite getting much less sunlight than we get now. The answer probably involves a much thicker greenhouse atmosphere then, with much higher levels of carbon dioxide and methane keeping heat trapped. But the relevant point here is just the brightening. The Sun has gotten about 30% stronger over 4.5 billion years, and it's still getting stronger. The current rate of brightening is roughly 10% per billion years, which sounds slow. Most things sound slow at that timescale, but the consequence of that brightening, applied to Earth's climate, is not slow at all. As the Sun gets brighter, the habitable zone moves outward. The orbital distance at which water can exist as a liquid pushes further from the star. The inner edge of the habitable zone, the line beyond which water would boil away under any reasonable atmospheric conditions, creeps outward year by year. Today, Earth sits comfortably inside the habitable zone. The inner edge is somewhere closer to the Sun than we are. In about 1 billion years, give or take a few hundred million depending on which model you use, the inner edge will reach Earth's orbit. That's not the end of life on Earth. The mechanics are more complicated than that. As the Sun brightens, the Earth's surface warms. The warmer surface causes more water to evaporate into the upper atmosphere. The water vapor in the upper atmosphere gets broken apart by ultraviolet light. The hydrogen escapes into space, the same kind of process that played out on Venus. The oceans start to lose water. The chemistry of the surface starts to change. The kind of life that requires complex multicellular bodies and stable temperatures and oxygen and liquid water all together starts to run out of places to live. Most credible models converge on a window of somewhere between 1 and 1.5 billion years from now, before complex life on Earth becomes untenable. Microbes might hang on longer. Microbes can do a lot. There are places on the current Earth where microbial life is going about its business at temperatures well above the boiling point of pure water, inside thermal vents on the ocean floor, in conditions that would kill almost everything else we know. Some of that life might survive for a while past the death of multicellular ecosystems, but the kind of planet we live on, the planet with forests and oceans and animals and rain and snow and seasons, that planet has roughly 1 billion good years left. If you push the timeline further, the situation gets worse. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin its red giant phase. The outer layers will swell outward. The Sun will get larger, much larger, hundreds of times its current diameter. The increased surface area will mean that even though the Sun's surface temperature will actually drop a little during this phase, the total energy output will go up by a factor of about 1,000. The orbits of the inner planets will be inside the expanding solar atmosphere. Mercury will be inside the Sun. Venus will be inside the Sun. Earth, by the most recent modelling done in the last few years, will most likely also be inside the Sun, somewhere around 7.5 billion years from now. Some scenarios let the Earth narrowly survive at the very edge of the red giant's atmosphere, scorched but not consumed, but the central estimate is that Earth gets eaten. So the planet itself has a kind of expiration date, and the habitability of the planet has a different, earlier expiration date. The way I think about the habitable zone is that it isn't a place, it's a moment. There's something I learnt to play years ago that helped me understand the habitable zone better than any diagram or article ever did. I learnt a little piano, just enough to make the easy songs sound right. And one of the first things you learn when you're learning piano is that the keys you can play with one hand are limited. You have an octave, 8 white keys, 5 black keys, all sitting within reach of your fingers when your hand is on the keyboard. If you want to play notes outside that octave, you have to move your hand. The habitable zone is the playable octave for liquid water. Within that range, you can do music. The notes work. Water exists in the form that supports life. Outside the octave, the notes are too high or too low, either too hot or too cold. The music falls apart. But the piano isn't stationary. Someone is slowly pushing it across the room. Or, if you prefer the actual physics, the playable octave is sliding outward over time. The keys you used to be able to reach keep falling off the edge of the bench. Mars's keys fell off the bench around 3.5 billion years ago. Venus's keys fell off the bench around 700 million years ago. Earth's keys are sitting roughly in the middle of the playable octave right now. The piano keeps moving, the keys keep sliding. There are other planets that we found in other systems that may already be past their playable octave. There are planets sitting in what we currently classify as the habitable zone of stars that have been around for many billions of years and have done their share of brightening and may have already shoved their habitable zone past those planets. We see them and we mark them down in the catalogue and we say liquid water could exist there. The truth is more complicated. Liquid water could exist there if the conditions are exactly right at the moment we're looking. The conditions a billion years ago might have been very different. The conditions a billion years from now will definitely be different. We're seeing a snapshot. The snapshot doesn't tell us how long the conditions have been that way or how long they'll continue. Habitable zone, in other words, has a built-in time problem that we usually ignore when we talk about it. A planet is in the habitable zone now. That doesn't mean it always was. That doesn't mean it always will be. That doesn't mean it ever supported life at any point in its history. The phrase carries a sense of permanence that the physics doesn't actually justify. There's a related point that's worth lingering on. The habitable zone is calculated in most models, assuming a planet has an atmosphere similar to Earth's. It assumes the planet has a magnetic field. It assumes the planet has stable rotation. It assumes the planet has water to begin with. None of those are guaranteed. Plenty of planets in the habitable zone have none of them. Plenty of planets that aren't in the habitable zone today might have had all of them in their past. The phrase habitable zone is shorthand for a much more complicated reality, and the shorthand can mislead. What's true is that the playable range exists for any given star at any given time. What's also true is that the playable range slides over time, and the planets it slides over are different at different epochs in a star's life. A planet that's a perfect candidate for life now might be a frozen wasteland a billion years from now, when the star has dimmed by the right amount to push the habitable zone closer in. A planet that's a frozen wasteland now might become habitable a billion years from now, as the star brightens enough to thaw it out. The galaxy is full of planets in the wrong place at the wrong time. That's the part that's hard to swallow. There are likely planets out there right now that had their best era a billion years ago and missed everything they could have been. There are likely planets out there that haven't started their best era yet and won't reach it for a billion years. The number of planets that happen to be in their habitable era right now, at this moment, is a small fraction of the total. We are one of them. The window is open here, the window is closed elsewhere. And that's just our star, a calm, well-behaved yellow dwarf, putting out energy at a steady rate with relatively few outbursts, lasting a long time. The Sun is by stellar standards an easy neighbour. Most of the stars in the galaxy are not like the Sun. Most of the stars in the galaxy are smaller, redder, and significantly less patient with their planets. Most of the planets we found, the ones in the so-called habitable zone, orbit stars that are not like our Sun. They orbit stars that, on a good day, are merely violent. On a bad day, they're worse than that. And every day on those stars looks like a bad day from a certain angle. That's where we have to look next, because most of the lottery tickets we have in the search for life are not the kind of ticket that pays out in the way we usually imagine. When most people picture a star with planets around it, they picture our Sun, a yellowish, steady, even-tempered star hanging there at the centre of the system, throwing off a comfortable amount of light, doing its job without making any fuss. That's what stars are supposed to look like in the cultural image. That's the kind of star you imagine when you imagine alien sunlight on an alien beach. That's not what most stars look like. Roughly 3 out of every 4 stars in the Milky Way are something called an M-dwarf, also called a red dwarf. These are small stars, much smaller than the Sun, ranging from about half the Sun's mass down to about 8% of it. They're cooler than the Sun, with surface temperatures somewhere between 2,400 and 3,700 Kelvin, compared to the Sun's roughly 5,800. Because they're cooler, they put out most of their light in the infrared, with the visible component leaning toward red, which is where the name comes from. They're dim, they're small. They're the kind of star that, if you replace the Sun with one, would leave the inner solar system in a permanent twilight. They are also, by a large margin, the most common kind of star in the universe. 3 out of every 4 stars you could ever visit in this galaxy are red dwarfs. 3 out of every 4 habitable zones being studied right now are around red dwarfs. 3 out of every 4 exoplanet announcements that include the phrase Earth-sized planet in the habitable zone are referring to planets that orbit red dwarfs. So when we talk about how many habitable worlds might be out there, we're mostly talking about red dwarfs by default. The math just works out that way. And that matters because red dwarfs are not gentle. Here's the part that takes a while to absorb. Smaller stars, like red dwarfs, have a few features that look like they should be friendly to life. They have very long lifespans because they burn their fuel slowly. The smallest red dwarfs are expected to last for trillions of years, far longer than the entire current age of the universe. They put out steady amounts of energy over those long lifespans. Their habitable zones are small and tight, which means a planet orbiting at the right distance to receive Earth-like amounts of energy from a red dwarf is sitting very close to the star, much closer than Mercury is to the Sun. The orbital periods of these planets are short. A year on a red dwarf habitable zone planet might last anywhere from a few days to a few weeks. The planets are easier to find because they pass in front of their host stars often enough that we get lots of opportunities to observe the transit. The signal is stronger because the planet blocks a larger fraction of the star's light. All of that is the good news. The bad news is that red dwarfs are magnetically furious. Smaller stars, in general, are more magnetically active than larger stars, especially when they're young. They produce more spots on their surfaces. They produce more flares. Red dwarfs have flares that can be, in some cases, 10,000 times more powerful than the most powerful solar flare our Sun has ever been recorded to produce. A flare that on the Sun would briefly knock out radio communications across half the Earth would, on a red dwarf, deliver radiation across the entire inner star system in concentrations that no biology we know would survive without serious shielding. And these flares aren't rare events on red dwarfs, they are routine. The TRAPPIST-1 system, which is 40 light-years away from Earth and is one of the most extensively studied red dwarf systems we have, contains 7 Earth-sized planets, several of which sit in the conventional habitable zone of their host star. It's one of the headline systems in exoplanet science. There are 7 rocky planets, more than one of which could in principle support liquid water around a single nearby star. It looks, on paper, like exactly the kind of place we'd want to look for life. In 2025, JWST observations of TRAPPIST-1 measured its flare activity over a sustained period and found that the star produces roughly 6 flares per day. 6 flares per day. Every day. That works out to over 2,000 flares per year, every year, for billions of years. The planets sitting in the habitable zone of that star, which orbit closer to it than Mercury orbits the Sun, are taking those flares full in the face, without any of the buffer space that comes from being far from your star. They are right next to the speaker. The volume is at maximum. The volume has been at maximum since the system formed. The volume will be at maximum for the rest of the star's life, which is to say, for trillions of years. What does that do to a planet? Laboratory studies have tried to simulate it. They've taken cultures of various Earth microbes, including the most radiation-tolerant ones we know about, like a bacterium called Deinococcus radiodurans, which can survive levels of radiation that would kill any other organism instantly, and they've exposed them to simulated red dwarf flare radiation at the doses the TRAPPIST-1 planets would actually receive. The conclusions vary by study. The general picture, though, is that flares of this magnitude, repeated at this frequency, are enough to sterilize all but the hardiest microbes from any unprotected surface. Anything sitting in shallow water, in topsoil, in exposed environments gets cooked. Some life might survive deep underground, in caves, in subsurface oceans below ice. But the kinds of habitable surface conditions that complex life on Earth depends on, the open sky, the running water, the photosynthesizing plants, are very hard to maintain on a planet that's getting hit with that kind of radiation every few hours, forever. There's another problem with red dwarf habitable zones, and that's tidal locking. Because the habitable zone around a red dwarf is so close to the star, the gravitational interactions between the star and any habitable zone planet are strong enough over geologically short timescales to lock the planet's rotation to its orbit. The same face always points at the star. The other face never sees the star. One hemisphere is in permanent day, baking under a red sun that never moves in the sky. The other hemisphere is in permanent night, cold enough that even atmospheric gases might condense and snow out on the surface. The boundary between the two hemispheres, the terminator, is a narrow strip of perpetual twilight where the day side meets the night side. That terminator is the only zone where the temperatures might be reasonable for surface water. It's a thin ring of habitability on a planet that's otherwise either too hot or too cold to support an ecosystem. There are models that suggest a thick atmosphere with the right circulation patterns could redistribute heat from the day side to the night side, evening out the temperatures and making more of the planet livable. There are other models that suggest the atmosphere on the day side might just slowly evaporate and migrate to the night side and freeze out there, leaving you with a planet that has a frozen ocean of nitrogen and oxygen on one hemisphere and no atmosphere at all on the other. Which model is right depends on details we mostly don't yet know about specific planets. The honest answer is that tidally locked habitable zone planets might be habitable in some cases, on the strip, with the right atmosphere, with the right luck. Or they might just be split planets, half ovens, half meat lockers, with a narrow band in between where nothing has the time to settle in. So when we count habitable zone planets in the catalogues, and we end up at numbers like tens of billions across the galaxy, we have to be honest about what that number means. Most of those planets orbit red dwarfs. Most of them are sitting closer to their star than Mercury is to ours. Most of them are getting hit with flares, many orders of magnitude more powerful than any flare our sun produces, several times a day for the entire life of the star. Many of them are tidally locked. The phrase habitable zone, as applied to these worlds, is doing some heavy lifting that it doesn't really earn. I keep coming back to this image when I think about it, and I think it captures the situation as honestly as I can. A red dwarf habitable zone is like trying to live inside a boxing ring while an opponent 4 times your size throws a haymaker at you every 4 hours for your entire life, for billions of years. You might still be standing, you might even be conscious, there might still be a body in the ring at the end of the round, but the word habitable is doing some heavy lifting in that sentence because the person who's standing has spent a lifetime taking blows that would have flattened most of the population by the 3rd round. That's most of the lottery tickets we have, 3 out of every 4. Most of the candidates for life that we're currently studying are sitting inside a fight that never ends. There are exceptions. There are red dwarfs that are quieter than the average, especially older ones, where the magnetic activity has settled down over billions of years. There are habitable zone planets around K-dwarfs and G-dwarfs, the kind of star our sun is, but those are less common and harder to find, and they're not where most of the existing observations are pointing. The porch light is still on around TRAPPIST-1. It flickers 6 times a day. The bulbs are unstable, the wiring keeps tripping. Every time you think you're about to see the house, the porch goes dark again, and then the surge comes back, and the light flares so brightly that for a moment you can't see anything else. That's what most of the lottery looks like. So we've now talked about a lot of dead worlds. Worlds where the conditions left, worlds where the star never let them settle, worlds in the wrong era of their host star's life, worlds whose habitability is on a moving target that's pushing past them. It's worth pausing here, because so far we've been talking about other people's deaths, other planets, other systems, other stars. The harder question is what Earth's own history actually looks like, because Earth, the planet that we usually treat as the steady one, the consistent one, the one that worked, has more endings in it than most people realize. The lights almost went out here, repeatedly. And once they almost went out because life itself learned to do something it had never done before. The standard story about Earth is that we got lucky. The sun is calm, the orbit is stable, the moon stabilized our axial tilt so the seasons don't go wild, the magnetic field holds, the atmosphere holds, the water holds, we had time, life showed up, life stuck around, and here we are, telling each other stories about how habitable our planet is because we get to. That story is true in its broad outline. Earth is, by every measure we can apply, an unusually steady world. We've had 4 billion years of conditions that allowed life to keep going, in some form or another, without ever fully resetting. That's not nothing, that's the biggest thing. But it's also not the whole picture, because Earth has come very close to going dark, more than once. The fossil record contains evidence of 5 major mass extinctions, plus a long list of smaller ones. These are events where so much of the world's biological diversity died off, in a geologically short window of time, that the fossil record itself becomes thin enough to fit in a much shorter section of any paleontology textbook. You can read the geological summary of a mass extinction in a single afternoon, even though the recovery from one took millions of years. There's a reason for that. There just isn't much to say. The fossils stop, the pollen stops, the microfossils stop, the carbon ratios in the rocks change, the lights, for a moment, go out. The 5 major mass extinctions are the Ordovician Silurian, around 444 million years ago, where about 85% of marine species disappeared. The late Devonian, around 372 million years ago, also taking out something like 75% of species. The Permian Triassic, around 252 million years ago, which is the worst one we know about. The Triassic-Jurassic, about 201 million years ago. And the Cretaceous-Paleogene, 66 million years ago, which is the one with the asteroid and the dinosaurs that most people learnt about in school. The Permian Triassic is the one that ought to make anyone uneasy. It's sometimes called the Great Dying because the numbers are so extreme. Roughly 96% of marine species died off in that event. Roughly 70% of terrestrial vertebrate species died off. Insects, which are notoriously hard to kill, had the only mass extinction event in their history during the Permian Triassic. The fossil record on either side of that boundary looks like 2 different planets. Almost nothing made it across. The trigger, by the best current understanding, was a massive series of volcanic eruptions in what's now Siberia, which pumped enormous quantities of carbon dioxide and sulfur compounds into the atmosphere, acidified the oceans, lowered ocean oxygen levels, and warmed the climate by something like 10 degrees Celsius in a relatively short window. It took the planet between 5 and 10 million years to fully recover ecological complexity after that. 5 to 10 million years where life on Earth was, in some genuine sense, on life support, hanging on, slowly rebuilding. That's the worst one we know about in the fossil record. But it's not the worst extinction event Earth has ever been through. The worst one happened so long ago that it almost doesn't have a fossil record at all. It happened to single-celled organisms in shallow seas more than 2 billion years before any of the famous extinction events that have names you might recognize. It's called the Great Oxidation Event, and it's the strangest catastrophe in the planet's history because it wasn't caused by an asteroid, or a volcano, or a comet, or a wandering star. It was caused by life itself. Here's how it went. For about the first 2 billion years of life on Earth, the dominant organisms were anaerobic. They got their energy from chemistry that didn't involve oxygen. There wasn't any free oxygen in the atmosphere to use. The early atmosphere of Earth was made mostly of nitrogen, carbon dioxide, methane, water vapor, and a few trace gases. Oxygen wasn't on the list because oxygen is highly reactive and tends to bond with other elements, and there wasn't anything around to make new free oxygen in significant quantities. The bacteria and archaea that lived on the early Earth used chemistry that we'd find profoundly strange today. They oxidized hydrogen, sulfur compounds, iron compounds, methane. They lived in deep ocean vents and in shallow tide pools and in stratified water columns. They were the entire biosphere. For about 2 billion years, that was what life on Earth looked like. Then a particular group of bacteria, the ancestors of what we now call cyanobacteria, evolved a new trick. They learnt how to do photosynthesis using water as the electron donor. That sentence is technical, so let me say what it actually means. They figured out how to use sunlight, water, and carbon dioxide to build sugars, and as a byproduct of that chemistry, they released oxygen. Free oxygen, pure O2 gas. It started slowly. The early oxygen-producing cyanobacteria pumped oxygen into the surrounding water, and the oxygen mostly got eaten up by chemical reactions with dissolved iron and other reduced compounds in the oceans. There was, for a long time, what geologists call an oxygen sink. The free oxygen was being produced, but the oceans absorbed it almost as fast as it came out. There's evidence of this in the rock record. The banded iron formations, those layered red and dark sediments you can find in places like Western Australia and northern Canada, are the fossilized fingerprints of that process. They're alternating bands of iron oxide and silica, deposited as the dissolved iron in the early oceans precipitated out as it reacted with rising oxygen levels. Each band is a chapter in a story about life slowly poisoning the chemistry of its own oceans. Eventually, the sinks filled up. The dissolved iron mostly precipitated out. The oxygen had nowhere left to go but up, so it started accumulating in the atmosphere. The atmospheric oxygen levels began to rise around 2.5 billion years ago. The rise started becoming significant. The Great Oxidation Event itself, the geological marker, gets dated to somewhere around 2.4 billion years ago, when the levels finally became high enough to leave a clear signature in the rock record. For most of the life on Earth at the time, that was a catastrophe. Oxygen, for an organism that evolved without it, is a poison. It's a reactive molecule. It tears apart cellular chemistry. The anaerobic microbes that had spent 2 billion years building up the entire biosphere of Earth were not equipped to handle it. They could metabolize a lot of strange chemicals, but oxygen wasn't one they had any tolerance for. The rise of atmospheric oxygen, in geological terms a slow process but in evolutionary terms a fast one, killed off something like 80 to 99% of life on Earth at the time. The number is hard to pin down because the fossil record at that age is thin, but the genomic and chemical evidence converges on it being a catastrophe of unprecedented scale. The first true mass extinction in the planet's history wasn't caused by a rock from space. It was caused by life learning to do something it had never done before. The first mass extinction was the air we now require to breathe. I want to sit with that one for a second. Everything you've inhaled today is part of the same atmosphere that 2.5 billion years ago was a planetary disaster. The oxygen that you need to keep your brain working is the same molecule that exterminated most of the planet's biosphere the first time it showed up at high concentrations. It was a poison in its day. It became a fuel later, after enough organisms evolved to handle it. The reason multicellular life is possible at all is that oxygen is energetically rich, and animals like us have metabolisms that can extract a lot of usable energy from it. None of that would have happened without the Great Oxidation Event. None of it would have happened without life nearly killing itself. The recovery from that event took a very long time. Between the Great Oxidation Event and the appearance of the first complex multicellular organisms in the fossil record, there's a stretch of about 1 billion years where the geological evidence is famously dull. It gets called by paleontologists the boring billion. There's not much going on in the rocks. Microbial life is around. It's quiet, it's catching its breath. The biosphere has been knocked back so hard that it spends 1 billion years just getting reorganized. Eventually, single-celled life learns to use oxygen efficiently. Eventually, eukaryotic cells appear with their internal organelles and complex chemistry. Eventually, multicellular life appears. Eventually, animals show up. But the time gap between the catastrophe and the recovery is enormous. The planet, in a real sense, almost stopped breathing 5 separate times in its history, and once the breathing itself was the thing that almost killed it. The atmosphere we now require to live is the same atmosphere that when it first appeared was an extinction event. That should change how you think about life on Earth. It changes how I think about it. The picture of Earth as a stable, life-friendly planet is true, but only in the broadest sense. Yes, the planet has supported life continuously for about 4 billion years. Yes, the conditions have stayed within a range that life, in various forms, could keep finding new niches inside. But within that broad continuity, there have been at least 5 major resets, plus the largest reset of all, the oxygen catastrophe. Almost everything alive has died, multiple times, in different ways, for different reasons. The thread of life on Earth is not a thick rope, it's a series of thin filaments, some of which broke, some of which survived, with the surviving filaments carrying everything forward each time. The relevance of all this to the question of life on other planets is straightforward but unsettling. If life on Earth, on the planet we're currently calling the success story, has almost been wiped out multiple times and once was nearly wiped out by its own metabolic byproducts, what are the odds that life elsewhere has navigated similar transitions successfully? What are the odds that a young planet, somewhere out there, evolved photosynthesis in some form and then choked on its own oxygen and never recovered? What are the odds that a planet developed a powerful volcanic episode, or a glaciation event, or an atmospheric shift, and the recovery never happened? We have one example of life that survived its own evolution. The fact that we exist means it can happen. The fact that it almost didn't on the only example we have means it might fail more often than it succeeds. That's a hard thing to know about your own planet. Earth nearly went silent. The fossil record gets thin enough, in places, to read in a single afternoon. All of which raises a different question. We've been talking about what happens to life once it gets going. We haven't talked yet about how often life actually gets going in the first place. And it turns out that's a question we don't have a good answer for either. We have exactly one example, and one example doesn't tell you much about how common the thing actually is. There's a tendency, when we talk about habitable planets, to assume that habitability and inhabitation are the same word. They are not even close to the same word. Habitability is a description of conditions. Inhabitation is a description of what's actually living there. The first is a kind of resume. The second is whether anybody ever showed up to do the job. Here's what we actually know about life starting on a planet. We know it can happen. We know it because we are on a planet where it happened. That's one data point. That's the entire data set. We do not know how often it happens on a planet where the conditions allow it. We don't know if it always happens, given enough time. We don't know if it usually fails. We don't know how to tell, from outside a planet, whether life ever appeared in it or not. We have hints. We don't have answers. What we do know is this. Earth had liquid surface water for somewhere between 100 million and 700 million years before there is any clear evidence of life. That's the gap between the planet being habitable and the planet being inhabited, on the only world we know that is both. Estimates of when Earth's oceans first stabilized as liquid water range from about 4.4 billion years ago, very early in the planet's history, to about 4 billion years ago, depending on which model you trust. Estimates of the earliest convincing evidence of biological activity range from about 4 billion years ago to about 3.5 billion years ago. So somewhere between 0 and 700 million years passed between Earth being capable of supporting life and Earth actually having life on it. That gap matters. It matters because we don't know what happened during it. Was life almost instantaneous as soon as the conditions were right, with the apparent gap just being an artifact of an incomplete rock record? Or did it take 500 million years of chemistry running and rerunning before the first self-sustaining biological system finally took hold? The answer to that question would tell us, more than almost anything else, whether life is common in the universe or vanishingly rare. The trouble is, we don't know. The earliest fossils on Earth are debated. The earliest biosignatures, like depleted carbon isotope ratios that biological metabolism tends to produce, are debated. The earliest microbial mats, called stromatolites, are debated. The earliest direct evidence of cells is debated. People publish papers refining these dates every year in both directions, and the field doesn't settle. The honest answer is that life on Earth got started somewhere between very quickly and very slowly, and we can't tell which. What we can do is look at how complicated the first step actually is. The transition from non-living chemistry to a self-sustaining, self-replicating, evolving cell is a hard problem to define, let alone solve. It requires a particular kind of chemistry. You need information storage, like DNA or RNA or something equivalent. You need a way to translate that information into action, like proteins or their equivalents. You need a way to enclose the system, like a cell membrane. You need an energy source. You need a way to make copies that are imperfect enough that variation can accumulate, but accurate enough that the system doesn't fall apart. You need all of those things in some form working together on a planet where they have time to assemble. None of that is trivial. There are biochemists who think the assembly of the first cell from prebiotic chemistry is a problem so hard that it might happen only once in the lifetime of an entire galaxy by sheer statistical chance. There are biochemists who think it's so favourable that it should happen on any planet with the right chemistry within a few million years. Both groups are smart. Both groups are working on the same evidence. They disagree because the problem is genuinely hard and the available evidence is genuinely thin. A good way to think about this is the difference between dropping a seed on bare stone and dropping a seed in good soil. If you drop a seed on bare stone, you can be pretty sure nothing will come of it. The conditions aren't right, the seed sits there, nothing happens. That's most of what we found in the exoplanet catalogue. The conditions are wrong. Whatever happened to the seeds, they didn't grow. But here's the part that takes a minute to absorb. Even if you drop a seed in good soil, you don't automatically get a tree. You might get a tree, you might get nothing. The seed might be the wrong species for the soil. The seed might be old. The seed might get eaten by a bird before it germinates. The soil might be good in all the ways you tested, but be subtly wrong in some way you didn't think to check. Conditions in good soil are necessary, but they're not sufficient. The seed has to actually take. Habitability is the soil. Whether anything actually showed up to grow in that soil is a separate question, and it's not one we know the answer to in any general way. The universe is dropping seeds across hundreds of billions of planets. We don't know what fraction germinate. We have one example of a tree, and we have no idea whether the field is full of other trees we just can't see, or whether the field is mostly empty soil with one tree standing in it. Mars is the most painful case to think about, because it sat there with everything it needed for a long stretch of time, and we still can't tell. Mars had liquid water for hundreds of millions of years. It had an atmosphere. It had a magnetic field for a while. It had the chemistry. It had the energy sources in the form of volcanic activity and hydrothermal systems. By every measure we can apply from a distance, Mars was a planet that should have been able to support life in the same era when life was getting started on Earth. Did it? We don't know. We have a tube, we have a rock with patterns in it that on Earth would be a textbook microbial biosignature. We have the careful language of the people who published the analysis, which is the language of suspicion rather than confirmation. We have, at the time of recording this, no way to bring that tube home, and the schedule for retrieving it has been stretched out into the late 2030s, possibly later. Even if we retrieve it, even if it comes back, even if the laboratory analysis confirms beyond reasonable doubt that the rock contains traces of biological activity from 3.5 billion years ago, that gives us a second example. 2 planets in one solar system where life appeared. From 2 examples, we still wouldn't know the rate at which life appears in the universe in general. We'd have a much better estimate. We'd have made one of the most consequential discoveries in the history of our species, but we'd still be talking about a single solar system. Venus is even worse. Venus may have had liquid oceans for 2 to 3 billion years. We can never check, in any meaningful sense, whether anything lived in those oceans. The surface of Venus today, with its acid clouds and lead melting temperatures and crushing pressure, is not a place that has preserved any biological record from the planet's habitable past. Whatever fossils Venus might have had, if it had any, have been baked, crushed, and chemically erased. Some of the most ambitious mission concepts for Venus involve atmospheric probes that could float in the upper cloud decks, where the temperatures and pressures are actually closer to Earth-like. There's even speculation about whether microbial life could survive in the cloud layer of Venus today, in the temperature zone about 50 kilometers above the surface, where the conditions are less extreme. But those are speculative searches. The historical record is gone. Then there are the worlds we haven't even talked about. Europa, Jupiter's icy moon, with a subsurface ocean of liquid water beneath a frozen shell maybe 20 kilometers thick. Enceladus, one of Saturn's moons, which is shooting plumes of water vapor into space from cracks in its ice-covered surface, indicating an internal liquid water ocean. Titan, Saturn's largest moon, with a thick atmosphere and lakes of liquid methane on its surface, and the possibility of exotic chemistry that might be a different kind of life entirely. There are places in our own solar system where the conditions exist for some kind of biology. We've barely begun to check. And then there are the exoplanets, 6,000 of them confirmed, hundreds of billions of them estimated. Even with the most ambitious telescopes we can imagine building, we will almost certainly never directly sample any of them. The light from those planets, after it travels light years to reach us, can be analysed for atmospheric composition. We can look for water vapor, we can look for oxygen, which on a rocky planet is a possible sign of photosynthesis. We can look for methane, we can look for combinations of gases that wouldn't naturally coexist in equilibrium, which would suggest something is actively producing them. That's the toolkit we have. It's a powerful toolkit, but it's a toolkit for reading fingerprints in air. It's not a toolkit for sending a tube down to the surface and bringing it back. So even with the best instruments we'll ever have, we may detect candidate biosignatures on dozens of exoplanets in the next few decades. We will probably never be able to confirm them by going there. We will be in the position we're in with Mars, but multiplied by hundreds. A rock we can't reach, a signal we can't follow up, a possibility we can't close. There's a thought experiment that helps me think about this. Imagine an alien astronomer, somewhere out there, studying our solar system from a few hundred light years away. They have powerful telescopes. They can detect the orbital signatures of all 8 planets. They can measure the atmospheres of the rocky ones. They look at Earth and they see oxygen, water vapor, methane, ozone, and other signatures that by their best models look like a biosphere. They write a paper. They publish a finding. They put Earth on the candidate list. What they cannot do is come here. They cannot send a probe. They cannot bring back a sample. The distance is too great. They will know Earth probably has life. They will not know what that life looks like. They will never be able to confirm it. They will spend the rest of their civilization's existence with Earth as a marker on a chart, an item on a list of candidates, a possibility they can't close. That's where we are with the 6,000, with the eventual 60,000, with the hundreds of billions. We will compile a list. The list will be partial. Some of the entries on the list will probably be correct. Some will be false positives. We will rarely have the luxury of finding out which is which. And the Mars tube, the one we drilled in July of 2024, the one we may not retrieve until the late 2030s, is the closest we will ever come to a real sample. That's it. That's the one. We have one tube. We can't get to it. Every other candidate world is much farther away, and the tube is the high water mark. The most consequential rock in our possession is sitting on the surface of another planet in a metal cylinder in the wind, and we may or may not be able to bring it home before the people who drilled it are retired. Which means that when we look up at the sky and we try to figure out who is or isn't out there, we have to be careful about what we're actually looking at. Because what we see from down here is not a snapshot of the universe as it is right now. It's a different thing, and once you see the difference, it's hard to unsee it. That's where we have to look next. When you walk outside at night, in a dark enough place to actually see the stars, what you're seeing is not the sky. You're seeing a record. Every point of light you can pick out, with the naked eye, or with binoculars, or with a telescope, is light that has been travelling at the speed of light for some amount of time before it hit your eye. The sun you see is 8 minutes and 20 seconds old. The moon you see is a little over a second old. The brightest star in the night sky, Sirius, is about 8.6 light years away, which means the light hitting your eye left Sirius 8.6 years ago. The next time you see Sirius, you're seeing what it was doing, give or take, around the time of an event in your life from almost a decade back. Whatever Sirius is doing right now, at this instant, won't reach Earth for another 8.6 years. Light is fast. Astronomically, light is slow. Proxima Centauri, the nearest star to the Sun, is 4.24 light-years away. The light you see from Proxima left in 2021 or 2022, depending on exactly when you're watching. The North Star, Polaris, is roughly 430 light-years away, give or take some uncertainty in the measurement. The light you see from Polaris tonight left it when Galileo was still alive, maybe even before. The brightest visible stars are mostly within a few hundred light years. The faintest naked eye stars stretch out to several thousand. Some of the stars you can see with binoculars are tens of thousands of light years away. The light from the center of the Milky Way, which you can see as a faint smudge on a dark night, left the galactic center about 26,000 years ago. The light from the Andromeda galaxy, the only other major galaxy you can usually see without a telescope, has been traveling for about 2.5 million years. The light from the Andromeda galaxy that's hitting your eye tonight left when our ancestors hadn't invented agriculture yet, hadn't invented language as we'd recognize it, hadn't really invented anything. Andromeda's light is older than humanity. Then there are the galaxies the James Webb Space Telescope has been finding at the edge of the observable universe. The most distant galaxies JWST has imaged sent their light out when the universe was less than 5% of its current age. That light has been travelling for more than 13 billion years to reach us. The galaxy that sent it has changed in ways we can't measure. It might still exist in some form, it might not. Whatever shape it's in now, we have no way of seeing the current version. We can only see the version from 13 billion years ago. So when you look up at the sky, you are, in a real sense, looking at history. The fact that this is technically true is something everyone has heard at some point in school. The fact of what it means to actually live in a universe like this is harder to absorb, because what it means is that the night sky is a postal system. Each point of light is a letter. The letters were mailed at different times. They arrived at your eye all together at this moment, but they were not sent at the same time. Some were sent yesterday, some were sent 1,000 years ago, some were sent during the Roman Empire, Some were sent before any of our ancestors stood upright. A few of them were sent by senders who, by the time the letter arrived, no longer exist. That last one is the part that takes a minute. Stars die. Not often in human terms, but constantly in galactic terms. There are stars in the night sky that, somewhere in the past few centuries or millennia, have ended. They have run out of fuel, collapsed, blown off their atmospheres, become white dwarfs or neutron stars or black holes. The transition can be slow in the case of a small star fading into a stellar remnant, or fast in the case of a supernova. Either way, the star you see now is not the star that's there now. The star you see now is a memory. The light is still travelling, will be travelling for years or centuries or millennia after the star itself is gone. There is, somewhere in the visible sky, at least one star whose light is on its way to your eye right now, even though the star it came from no longer exists in any form we'd recognise. You can't tell which star. You can't tell from the envelope. The letter looks the same as the letters from senders who are still very much alive. You only know that some of them are from senders who aren't. The sky we see is, in a real sense, a memorial. I want to push that thought further because it connects to everything we've been talking about tonight. Every habitable planet we have detected, or might detect in the coming decades, is also a letter from the past. The light from a planet around a star 50 light-years away is 50 years old by the time it reaches us. That means the atmospheric composition we measure is 50 years out of date. A planet around a star 100 light-years away, 100 years out of date. A planet around a star 1,000 light-years away, 1,000 years out of date. That doesn't sound like much for a planet. Atmospheric composition tends to change slowly. A few hundred years here or there, on a world that has been around for billions of years, shouldn't matter much, and mostly it doesn't. But when we get to the edge of what we can plausibly detect, or when we start asking whether any specific planet is currently inhabited, the time lag matters. The light from a planet 10,000 light-years away tells us what its atmosphere looked like 10,000 years ago. Civilizations rise and fall in less than that. If there was a technological civilization on a planet 10,000 light-years away, and that civilization existed for say 5,000 years and then collapsed, and the collapse happened 9,000 years before the light we're seeing left them, then we might be looking at the light from a still active civilization. If their civilization had collapsed 11,000 years ago, we'd be looking at light from after they were gone, and we'd see no signature of them at all. Whether anyone is out there right now is a question we cannot directly answer. We can only ask whether anyone was out there at the moment when the light left them. We cannot ask about now. The concept of now, applied to a star system thousands of light-years away, doesn't have meaning in a way we can investigate. Now is a local concept. The universe doesn't really have a global now. So when we look up at the sky and try to figure out who is or isn't out there, we are in a real sense opening a mailbox full of letters of different ages, from different senders, with no return address dates we can fully trust. Some of the letters are from people who are still home, some are from people who have moved, some are from people who died long before the letter arrived. We sort through them, we do our best, we make our maps. The maps are useful. The maps are also, fundamentally, maps of a place that may or may not still exist in the form the map describes. This connects to the harder thing, the thing we've been circling around all night. The universe might not be empty. It might be a graveyard. Many of the lights you can see could be coming from places where life happened and then ended, long before that light started its journey toward you. The deaths could have happened so long ago that the news hasn't reached us yet. The news is on the way. The news is 50 light-years out, or 100 or 1,000, travelling at the only speed information can travel through this universe. We will get the news. We won't know when. We'll see a star, and we'll measure its planet, and we'll find a signature that looks like life. The signature will be a fingerprint from a planet that may not have had life for a long time by the moment we're measuring, and we won't be able to tell. The honest version of stargazing, the one that takes the physics seriously, is that we are reading mail. Some of the mail is recent, some of it is old, some of the senders are still home, some are not. The mailbox is enormous. The letters never stop arriving. You can spend a lifetime sorting through them. You'll never finish. There's a particular feeling that comes with this. Late at night, when you let it really sink in, you step outside, you look up, you find a bright star. You let your eye rest on it for a minute. You think about the years that light has been traveling. You think about what was happening on Earth when that light started its journey. You think about what was happening on the planet that sent it. If there was a planet, if there were any inhabitants, what they might have been doing on the day that particular photon left them on its long trip across the dark. And then you realize that the photon is just one photon out of trillions arriving at your eye every second. Every star is sending letters constantly. The mailbox is full beyond comprehension. Every glance at the sky is a glance at more mail than you can ever read. Some of it is from senders who are still alive. Some of it isn't. You can't tell the difference. Not from down here. Not yet. Which leaves one last thing we have to talk about. The one part of the sky we can actually do something about. The one we're standing on. There's an instinct, when we talk about all of this, to position Earth as the exception, the one that worked, the lucky planet, in the lucky orbit, around the lucky star, with the lucky moon, with the lucky magnetic field, with the lucky atmosphere, with the lucky biology. Everything broke our way, everything held together. We get to sit here, 4 billion years into this, breathing the same air that almost destroyed the biosphere when it first appeared, looking up at planets that didn't make it, and feeling, on some level, that we are not on the same list as them. We are on the same list as them. Earth is not the exception. Earth is the one in the middle. Earth is at the part of the story where the lights are still on but the timer is running. The fact that we exist at this particular moment is not because Earth is a different kind of world than Mars or Venus. It's because we showed up at the right time. We are inside a window. The window is open right now. The window will close. Let me lay out the numbers because they're not abstract, they're specific. Earth formed about 4.5 billion years ago. Liquid water on the surface goes back at least 4 billion, possibly 4.4 billion years. Life shows up in the rock record somewhere between 3.5 and 4 billion years ago. Complex multicellular life shows up around 600 million years ago. Animals with hard parts, around 540 million years ago. The first land plants, around 470 million years ago. The dinosaurs, between 230 and 66 million years ago. Modern humans, about 300,000 years ago. The agricultural revolution, about 12,000 years ago. Modern industrial civilization, about 200 years ago. That's the history. That's where we've been. Now look forward. The sun, as we talked about earlier, has been brightening at a rate of roughly 10% per billion years. The brightening continues. Multiple lines of evidence and modelling converge on a window of somewhere between 1 and 1.5 billion years from now, before the conditions on Earth become too hot for complex multicellular life to keep functioning. That doesn't mean the planet becomes uninhabitable instantly. It means the slow process of warming, evaporation, atmospheric loss, and oxygen decline crosses a threshold past which the kind of ecosystems we recognise cannot keep going. The oceans will be evaporating. The plants that need stable temperatures will struggle. The food chains that depend on those plants will struggle. The animals at the top of those food chains, including any version of us, will be in trouble. Microbes might hang on past that point. There are organisms on Earth right now that thrive in conditions that would kill almost everything else. They live in deep rock, in superheated water, in the chemistry of subsurface aquifers, in extreme environments where the conditions of the surface stopped mattering long ago. Some of that life might continue to exist for hundreds of millions of years after the surface becomes uninhabitable for everything else. Earth's biological history might end with the same kind of organisms it started with. Microbes in the dark, quietly carrying on, in environments that no longer have a sky above them worth looking at. That's the first phase of the ending. Sometime between 1 and 1.5 billion years from now, the surface stops being a place for complex life. The biosphere collapses, the atmosphere starts changing, the oceans begin to disappear. The same kinds of processes that played out on Venus, on a different timescale and through a different mechanism, begin to play out here. In about 3 to 4 billion years from now, the Earth's surface temperature is high enough that the oceans are essentially gone. The atmosphere is thinning, the carbon dioxide levels are climbing, the planet is in slow motion becoming a hotter, drier, more hostile version of what it used to be. The dynamic geology of plate tectonics depends on water at the surface and in the crust, and as the water leaves, the geology starts to grind to a halt. Earth, by this point, would not look anything like the Earth we know. The continents would still be there, the mountains would still be there, the oceans would not. In about 5 billion years from now, the Sun runs out of hydrogen in its core and begins its red giant phase. The Sun's outer envelope expands, Mercury is swallowed, Venus is swallowed. By the most recent modelling, including a series of papers from the last few years that have refined the calculation by accounting for solar mass loss and tidal interactions, the central estimate is that Earth too ends up inside the expanding Sun. Some studies suggest the Earth's orbit might migrate outward enough to escape the expanding Sun's outer layers, leaving behind a scorched, airless rock circling a slowly cooling red giant. Other studies suggest the orbital drag from the expanded solar atmosphere brings Earth inward and consumes it. The central estimate, for what it's worth, is that Earth doesn't make it. The likely engulfment timeline is somewhere around 7.5 billion years from now. That's the date most commonly cited. The actual physics involves more uncertainty than that suggests, but 7.5 billion is the working number. So here's the full window. Earth has been habitable for approximately 4 billion years. Earth will be habitable for approximately 1 to 1.5 more billion years. The total window of habitability for this planet, from start to finish, is somewhere between 5 and 5.5 billion years. We are, demonstrably, past the middle. I want to say that one more time, because it's the part that's hard to hear and easy to skip over. Earth's total window of habitability is about 5 to 5.5 billion years long. We are currently somewhere around 4 billion years into that window. We have somewhere between 1 and 1.5 billion years left. The largest portion of Earth's life-bearing history is behind us, not ahead of us. That's not a doomsday claim. It's not next week. It's not in any time frame that should affect any decision any human being makes about anything in their actual life. A billion years from now is so far in the future that the continents themselves will have rearranged into shapes nobody alive today would recognize. Whatever exists on Earth in a billion years will be as different from us as we are from the first eukaryotic cells. The species we are won't be here. The civilization we have won't be here. The languages we speak won't be here. The Earth itself will only barely resemble the Earth we know. But the planet's own trajectory, the long arc of the planet itself, is past the middle. Earth is not in its morning. Earth is in its late afternoon. The evening hasn't started yet, but it will. The window is open. The window won't be open forever. That's the third unsettling thing I wanted to leave you with. Not because it's frightening. It's just true. Earth is not, in the long arc of itself, the exception. Earth is the one that's currently demonstrating what habitability looks like in the part of the story where it's actually happening. Mars showed us what comes after. Venus showed us what comes after a different version of after. Earth is showing us what during looks like. The during is the whole point. The during is what makes the universe interesting when it happens. The during is rare, by our best guess, both in space and in time. Earth's atmosphere, in the far future, will go through its own escalation and eventual loss. Different mechanism than Mars, but the ending rhymes. The sun brightens, the upper atmosphere heats. Water vapor gets transported high enough that ultraviolet light breaks it apart. The hydrogen escapes to space. The oxygen gets sequestered into rocks or burns off. The atmospheric pressure drops. The magnetic field, depending on the future evolution of Earth's interior, may or may not weaken at the same time. The end state of Earth, in 3 or 4 billion years, looks like a less extreme version of Mars or a less extreme version of Venus, depending on which physics wins. Either way, the destination is similar: a dead world with a thin or absent atmosphere, no liquid surface water, no biosphere, orbiting a star that is also nearing the end of its main sequence. Remember how Mars lost its atmosphere? The shield went down, the wind picked at the air, the pressure dropped for hundreds of millions of years. Mars, in a real sense, is what Earth is in the process of becoming, just along a different timeline. Mars was the dead other when we started tonight. Mars is also the preview. The way I've come to think about all of this is as a long evening. The day is over. The evening is here. The light is still warm. The window is still open. The night is coming, but the night is not here. We get to sit on the porch of this planet, while it's still possible to sit on the porch of this planet and watch the sky and read the letters and try to figure out who else, somewhere out there, might also be sitting on a porch while their light is still warm. The window won't stay open. That's true. It's also true that the window is open now. Both things are true at the same time. The thing about a window being open is that what matters is whether it's open in the moment you're standing in. Earth's window is open. The oceans are still liquid. The air is still breathable. The magnetic field is still up. The planet is still doing the work of being a planet that supports life. None of that is broken. If I had to choose an image for this part, it would be the feeling you have on a particular kind of evening. The kind of evening where the air is finally cool after a hot day, where the light is going golden, where you know it's going to get dark but it isn't dark yet, where you can sit outside and not feel cold and not feel hot, and the world is doing its small, ordinary things around you. That kind of evening doesn't last. It can't. The dark is coming. But the dark isn't here. That's the moment we live in. Earth is having one of those evenings. The evening is several 100 million years long. We get to be inside it for a sliver of that span. The evening is good. The evening is warm. The evening is going to end. None of those facts cancel each other out. There's something genuinely strange about being the species that figured out the timeline. None of the other animals on this planet have any idea that this is happening. The dolphins don't know. The crows don't know. The trees don't know. Only we have done the math. Only we have looked at the rock record and the stellar physics and worked out, with mathematical specificity, where we are in the long arc of our own world. That knowledge is recent. People have only known this, with anything like the precision we have now, for a few decades. The implication of it is just starting to filter down into the broader culture. Most people don't know yet. Most people still imagine Earth as the steady, permanent thing. You knowing it is part of why this matters. Because once you know, the night sky becomes something different. Once you know, the porch light becomes something different. Once you know, the question of whether anyone else is out there becomes something different. It becomes less a question of how many neighbours we have, and more a question of which ones still have their light on, and which ones used to, and which ones never did, and which ones might be reading their own version of this sky right now, looking back at us, wondering the same things. The porch light is still on here, for now. I want to spend a little more time in the place we've arrived at before we close the night, because the texture of it matters. The shift in how you see the sky is the actual thing this whole conversation is about. The facts are scaffolding. The shift is the building. When you absorb that most habitable windows close, and that most stars are not gentle, and that most planets are nothing like ours, and that even ours is well past the midpoint of its arc, you stop seeing the night sky as a question about who might be out there. You start seeing it as a question about when. When did the conditions arrive on each of those worlds? When did they leave? When did anything take advantage of them? Are any of those worlds doing right now what Earth is doing right now? Are any of them, somewhere in their own equivalents of a long evening, also looking back across the dark at lights that may or may not still have someone behind them? That's a different way to think about the sky. It's less a search for company, it's more a survey of times. Some of which overlap with ours, most of which don't. The galaxy, in this picture, isn't a city of neighbours, it's something more like an archive of moments. Each star and each planet is its own slice of time, with its own beginning, its own duration, and its own end. The slices don't usually line up. The galaxy is full of lives that started before us, ended before us, started after us, will end after us. We're walking through the archive. We can't see most of it. We can only see the slices whose light happens to reach us now, and we can only act on the ones we can study with the tools we have. That's not depressing when you sit with it long enough. It's actually clarifying. The standard framing, which is either we are alone or we are surrounded, is a binary that doesn't really fit the universe we live in. The real situation is that we are inside a moment, and other moments have happened, and other moments will happen, and the question of whether we have company isn't about presence or absence in some absolute sense. It's about overlap. The overlap is what we never have a great instrument for. Time is harder to measure across light years than distance is. A star's spectrum tells you what the star is made of and how hot it is. The transit signature of a planet tells you how big it is and how close it is. The atmospheric spectrum, if we can measure it, tells you what the planet's air is made of. None of those measurements tells you when, in the planet's own history, the snapshot was taken. You're always looking at a moment, you're always missing the timeline. Which means that the question of whether the universe is empty has a quiet answer we don't usually consider. The universe might be empty in the sense of right now. The universe might be full in the sense of all time. Both of those can be true at the same time, depending on how you take the snapshot. And the snapshot we get to take is the one available from our position, with our instruments, in our particular slice of time. Here's what I find myself coming back to, late at night. The fact that there have probably been worlds where life appeared, lasted for some span of time, and ended, is one of the most quietly profound things our species has worked out. It's a sentence that wasn't really sayable, in any rigorous form, until the last several decades. Before then you could speculate, you could write science fiction, you could imagine. You couldn't really argue it from the physics. Now we can. The physics doesn't quite force the conclusion, but the physics now supports it strongly enough that you can build a coherent picture out of it. Worlds happen, then they stop happening. The universe is in the business of producing places where the lights come on, run for a while, and go out again. Some of those places, on the few we've gotten close enough to study, may have had life. Some of those places may have had nothing. Some of them may have something right now, in their local now, that we won't know about for 1,000,000 years because the light hasn't reached us yet. That's the universe. That's what's actually out there. The night sky isn't a void. It isn't a crowd. It's an archive of long evenings in different stages of the same long story, with our particular evening currently happening here. There's something else I want to say, because it's been sitting with me through this whole conversation, and it's the part that doesn't make it into most of the science. The fact that Earth is past the middle doesn't change anything about how good the evening still is. The evening is still warm, the kitchen window is still lit, the voices inside the house haven't stopped, the seasons still come, the rain still falls, the stars still come out at night. Whatever's coming is coming. Tonight isn't that. Tonight is one of the nights inside the open window. If you've been listening this whole time, you might have started to feel a particular kind of quiet settle in. That quiet is not pessimism. It's not optimism either. It's something else. It's what you get when you let the actual scale of the situation arrive, without trying to make it into something more comforting or more frightening than it is. The universe has been running for 13.8 billion years. The Earth has been around for 4.5. Life has been around for 4. We've been around for 300,000. Civilization for 10,000. We're a sliver of a sliver. The slivers before us are gone. The slivers after us aren't here yet. The sliver we are inside is the only one we get to experience directly. And the sliver is warm, right now, tonight. I think that's the closest I can come to saying what this is actually about. It's not about being scared. It's not about being awed. It's about noticing where you are. Earth, in this moment, is doing the thing planets only get to do for a thin slice of their existence. It's hosting life. It's supporting weather. It's holding an atmosphere. It's keeping water liquid. It's spinning at a stable rate. It's protecting itself with a magnetic field that's still up. It's giving us the kind of night where you can step outside and see the sky and not freeze and not boil and not suffocate. That's the gift. That's the only gift the universe ever gave us. Everything else is a consequence of that gift. Mars used to have something close to this. Venus had it for longer. Both of them lost it. The mechanism by which they lost it was different in each case, but the result was the same. The window closed. The lights inside went out. The porch lights are still on, in the sense that the sun is still shining on those worlds. Nothing else is on. The houses are dark. We've been knocking on Mars for 60 years. We've barely begun to knock on Venus. We will probably never knock on most of the other worlds. The knock takes too long. The distance is too great. The instruments are still being built. But there's a knock we can hear right now, the most useful knock of all, and it's the one that has nothing to do with other worlds. It's the one coming from this one, the wind. The trees, the rain on the roof if you're somewhere where it rains, the breathing of the person beside you, if there's a person beside you, the hum of a refrigerator, the distant sound of a road, the clock ticking. Whatever's making any noise in your room right now is the sound of a planet that's still alive. That sound has been continuous, in some form, for 4 billion years. The sound is the gift. The sound is what we mean by habitable. The sound is going to stop, eventually. Not for you, not for anyone you'll meet, not for any version of any civilization that any human will ever build. But, in the long arc, it's going to stop. The planet will go quiet. The wind will keep blowing for a while after that, but it'll be moving a different atmosphere, on a different planet that just happens to have the same name. The continuity won't be biological, it'll be just geological. The rocks will remember us in some form, in fossils that may or may not be readable by anyone or anything. We will become the layer in someone else's deep history. That's all eventual. It's not now. Now the porch light is still on. The kitchen is still warm. The window is open. That's where I want to end the long part of the night. With the window open, with the porch light on, with the gift still going. There's one last thing I want to say before we close, and then we'll be done. If you stayed with me this far, you've heard about Mars and Venus and worlds we will probably never set foot on. You've heard about life killing itself by learning to breathe. You've heard the strange and very quiet fact that Earth, the warmest house in the neighborhood, has its porch light on a timer. There's something I want to leave you with, and it isn't a fact. When we look up, we tend to imagine the universe is either teeming with company or completely alone, crowded or empty. But there's a third possibility, and it might be the truest one. The universe could be neither. It could be a place where life happens and then doesn't, where worlds get their billion good years and then go quiet, where the porch lights stay on long after everyone has gone home. That doesn't make us less rare. If anything, it makes us more so. Not because nothing else ever made it, because something else once did, somewhere, and stopped, and we are still here, for now. Earth's window is open. The window won't be open forever, but it's open tonight. The oceans are still liquid, the air is still breathable, the magnetic field is still up, the geological clock that keeps the carbon dioxide cycle balanced is still running, the species are still adapting, the seasons are still turning, The thing that planets only get to do for a sliver of their lives, the thing called supporting life, is something this planet is currently doing. You are an example of that. You're reading this, or listening to this, or drifting towards sleep with this in the background, because Earth is at this moment allowing it. Somewhere on a world we haven't found yet, the same conditions may be true tonight, and someone on that world might be looking back at a sky that includes our sun, wondering the same thing you're wondering. Maybe they're putting it into words in a language that has nothing in common with ours. Maybe they're not using words at all. Maybe they just have an internal sense, in whatever counts for them as awareness, that the night is large, and that they are a small part of it, and that something might be looking back. Or maybe they're not. Maybe their lights went out a long time ago and we haven't noticed yet. Maybe the light we'd need to see them, to confirm they were ever there, is still on its way to us, taking centuries or millennia to make the trip. Maybe by the time we get the message, the senders won't exist anymore, and we'll have to figure out from the message alone what they meant. Maybe nobody is out there at all, and the universe is empty in the way the loudest version of the loneliness argument claims it is. Maybe Earth really is the only place where the chemistry came together. Maybe we are, in a literal sense, the only living thing in this galaxy, or in any galaxy we'll ever see. That last one is a possibility you can also sit with. It doesn't have to be the most likely answer. It just has to be allowed. The fact that we don't know is the actual situation. Not knowing is not a problem to solve tonight. It's a place to sit for now until more information comes in. Some of it will, some of it won't. The universe is patient. The universe is also old enough that it can afford to be patient. We have less time than it does, but we have enough time for tonight. Either way, the porch light is still on here. The sky is still up there. The numbers still work. The water is still liquid. The lungs still breathe. The rocks under your feet are still old enough to remember things you can't imagine, and stable enough to keep doing the slow work of holding the planet together for another billion years, give or take. Mars's porch light is still on, in the technical sense that the sun still shines on Mars, even though the house is empty. Venus's porch light is still on too, in its own way, behind sulfuric clouds, on a planet that is glowing hot under a sky that is heavy and dim. TRAPPIST-1 is still flaring 6 times a day. The library is still standing, with its lights mostly out and its shelves still full. The mailbox is still receiving. And here tonight, you're inside a moment that most planets never get to have at all. You don't have to do anything with that. You don't have to feel awe or sadness or anything in particular. You can just notice it. The window is open, you're in the room, the light is warm, the night will end the way nights end. The morning, if there is a morning where you are, will come. The seasons will keep turning. The Earth will keep doing what it's been doing for 4 billion years, for as long as it can. The lights are on here, for now. If I had to give you one thing to take with you from all of this, it wouldn't be a fact. The facts are out there. You can look them up. The number of confirmed exoplanets will change between when this is recorded and when you hear it, because new ones get added every month. The exact age of Mars's magnetic field will get refined by the next paper. The Venus models will get adjusted. The estimate of how long Earth has left will move by a few 100 million years in one direction or the other, depending on which model team has the latest run. The numbers are not the point. The point is the shape of the picture they make when you put them all together. The shape is something like this. The universe makes worlds. The worlds get a window. Some of the worlds use the window. Most of the worlds don't, as far as we can tell, but our ability to tell is limited. The windows close. The worlds keep existing in some form after the windows close, but they go quiet. The galaxy fills up, over time, with quiet worlds whose windows have already shut. The few worlds whose windows are open right now are scattered through the dark, separated from each other by distances and times that make finding each other extremely hard. Most of them will probably never find each other. We are one of those worlds. right now, tonight, for a window that is wider than any individual life can use, but narrower than the planet's own history. We are inside the gift. The gift is the only one we ever got. The gift is enough. Sleep well.